Have you ever wondered why you would weigh significantly less on the moon, even though you're still the same person with the same body? Today, we are diving deep into the science of physics to learn exactly how to calculate weight and understand its relationship with mass. While we often use the terms mass and weight interchangeably in daily life, in science, they are two very different things. Mass is the actual amount of matter in an object. It's determined by the total number of atoms that make up a physical body. Because it's a measure of the stuff inside you, mass is an intrinsic property. It stays the same whether you are on Earth, the moon, or deep space. Weight, on the other hand, is a measure of the gravitational force acting on that mass. It is a vector quantity, meaning it has a direction, straight down. Unlike mass, weight is variable. It depends entirely on the strength of the gravitational field where you happen to be standing. To calculate weight, we use Newton's second law of motion. The formula is simple. Weight equals mass times gravity, or W equals m times g. In this equation, W stands for weight. In the International System of Units, weight is measured in newtons, abbreviated as a capital N. The m represents mass, which is measured in kilograms. Remember, always use kilograms in this formula to get the correct result in newtons. Finally, g is the acceleration due to gravity. This is the rate at which an object speeds up as it falls toward the center of a planet. On Earth, the standard value for g is approximately 9.8 meters per second squared. This is the constant we use for most everyday calculations. Let's try a practical example. Suppose you have an object with a mass of 50 kilograms. Let's calculate its weight on Earth's surface. We multiply 50 kilograms by 9.8. This gives us a result of 490 newtons. That is the gravitational force Earth exerts on that object. That weight is what you actually feel as heaviness when you try to lift something. The more mass or the stronger the gravity, the heavier it feels. Understanding this is crucial for engineers and scientists. They must calculate weights to build safe bridges, elevators, and even spacecraft. If you ever need to perform these calculations quickly or convert between units, check out the specialized tools at everythingcalculators.com. Now, let's see what happens when we leave Earth. Because different planets have different sizes and masses, their gravity varies significantly. Take Mars, for example. It's smaller than Earth, so its gravity is weaker, only about 3.7 meters per second squared. Our 50-kilogram object would only weigh 185 newtons on Mars. You would feel much lighter and could jump significantly higher. The Moon is even smaller. Its gravity is roughly 1/6 of Earth's, at approximately 1.6 meters per second squared. On the Moon, that same 50-kilogram mass weighs a mere 80 newtons. This is why astronauts can bounce around so easily during lunar missions. Notice the trend. The mass stayed at 50 kilograms every single time, but the weight changed based on the environment. On the opposite end, the Sun has massive gravity, about 274 meters per second squared. You would weigh over 27 times more there than on Earth. What about weightlessness? You've seen astronauts floating in the International Space Station. Does that mean gravity is zero there? Actually, gravity at the ISS altitude is still 90% as strong as on the ground. The floating happens because of a state called free fall. The station and the astronauts are falling toward Earth but moving sideways so fast that they keep missing it, creating the sensation of zero weight. Even on Earth, weight isn't perfectly constant. Because the Earth bulges at the equator, you are slightly closer to the center at the North Pole. You actually weigh a tiny bit more at the North Pole than at the equator, even though your mass hasn't changed at all. We can also use the formula to find mass if we already know the weight. We simply rearrange it to mass equals weight divided by gravity. If an object weighs 980 newtons on Earth, what is its mass? We divide 980 by Earth's gravity of 9.8. 980 divided by 9.8 equals 100. So, the mass of that object is exactly 100 kilograms, simple and consistent. It's important to note the different measurement systems. In the SI system, we use kilograms and newtons, but in the US, things are a bit different. In the Imperial system, the pound is actually a unit of force or weight, not mass. The corresponding unit of mass is called a slug. External factors like buoyancy can also affect measurements. A helium balloon has mass, but its weight might appear negative because air pushes it up. Scientists also distinguish between inertial mass, how hard it is to push something, and gravitational mass. Luckily, they are always identical in value. Let's recap. Mass is the amount of matter and never changes. Weight is the force of gravity acting on that matter and changes based on location. The formula to remember is weight equals mass times gravity. On Earth, always use 9.8 for your gravity constant to get accurate results. For more physics tools and easy-to-use calculators, make sure to visit everythingcalculators.com. It makes these complex calculations a breeze. You can find the link to the calculator in the video description and the first pinned comment. Thanks for watching, and stay curious.